Okay, so today we're going to talk about restriction enzymes, which is another molecular tool that scientists use. Sorry, I have a little bit of a sore throat, so I sound a little different today. Hopefully you can still hear me. Okay, so here we go. I think this is on page 53 of your notes, but you should have been told before this what page to start on. So you can think of molecular restriction enzymes like molecular scissors. Essentially what a restriction enzyme does, and it's technically called an endonuclease, is it cuts DNA at very specific sequences. So it doesn't just chop the DNA up anywhere. It's recognizing, it's looking for a specific sequence, and it's going to cut at a particular location within that sequence. So let's take the time right now to apply that to some things we already know. Take a minute, talk to your neighbor about what kind of bonds are broken then when a restriction enzyme cuts. The types of bonds that are broken when a restriction enzyme cuts are actually covalent bonds within that single strand of DNA. See, right here, right, we're actually going to break that covalent bond right here. Now, a lot of you may have said hydrogen, which is a naturally good answer too. But hydrogen bonds actually are sort of like an indirect result of restriction enzymes acting. Because if you have the two single-stranded pieces, the single-stranded piece being broken apart, then the hydrogen bonds between the two strands will actually break as a result of the two single strands coming apart. So it's sort of an indirect result. But what the restriction enzymes actually cut are or break are covalent bonds. So these bonds right here are what are broken. But as a result of that, because the two strands of DNA now can't stay together, hydrogen bonds will also break. So restriction enzymes are actually naturally occurring in bacteria. Different types of bacteria have different restriction enzymes, and their names actually come from which bacteria they were discovered in. Bacteria actually use restriction enzymes as a way to protect themselves from foreign invading DNA. That being said, since the restriction enzyme's job is to look for a sequence and then cut in that location, it's possible that a bacteria's DNA could have that sequence too, right? And it wouldn't want to cut up its own DNA. So bacteria actually do have mechanisms, molecular ways that they protect their own DNA from getting cut up by their own restriction enzymes. Now, the reason I said that restriction enzymes are a molecular tool is because since discovering them, scientists have now been able to isolate them from the bacteria, purify them, and now they're actually sold for use in lab work. So if I know I want to cut a particular sequence of DNA, I can find out if there is a restriction enzyme that will match it, and you can purchase that and use it so that you can cut your DNA in a very directed fashion. You have this table in your notes. Don't worry too much about it. It's really just meant to show you some of the really common restriction enzymes and just give you an example of the fact that they don't all cut in the same location. So in this diagram, you can see that they all recognize a different sequence, and then the place that they cut is actually the bond between the two blue bold bases. So EcoR1 cuts here between the G and the A, TAC1 cuts between the T and the C, Hindi3 cuts between the A's, BAMH1 between the two G's, etc. Okay, you definitely don't need to memorize this or anything like that. This is just meant to give you an example of how each restriction enzyme cuts in a different specific location. What I do want you to know about is the types of cuts that they make. If you go back for a second, you can see that here, if it cuts here and here, right, it would kind of make like a zigzag cut. Whereas if you go down here to the ALU1 cut, it would be straight down. So the difference between are what they call sticky ends versus blunt ends. So when a restriction enzyme is cut, they either produce sticky ends, which means there's going to have a little overhang at the end. That zigzag cut creates kind of like these little single-stranded sections at the ends. Those we call sticky ends. Or a blunt end would be like the alu one, which is just a straight chop all the way down. The reason this is significant is because these sticky ends have become very useful to scientists as they've found uses also for restriction enzymes. Because remember, a sticky end is not truly sticky, but we call it sticky because it's single-stranded. That means it has the ability to hydrogen bond to another single-stranded piece of DNA. And that's actually the key here. So let's take a look at how we can put this together and apply it and use it for molecular technology. Recombinant DNA. Remember, we talked about how we have these plasmids and they're naturally occurring, but that essentially scientists have been able to doctor them, to fix them up in such a way where they can contain whatever gene we want. So we're kind of going backwards now from the background in the GFP lab, because what we're looking at is like, well, how do you make those plasmids that don't normally exist in nature? And the answer actually is restriction enzymes. We can create recombinant DNA, meaning essentially man-made cutting and pasting of DNA, using restriction enzymes. The key is this. If I want to stick two pieces of DNA together, one of the most important things I need to do that is actually to cut them both with the same restriction enzyme. I want you to take a minute and talk to your neighbor about why. Why might that be? Why can't I just cut them with any old restriction enzyme, two different ones for that matter? Why is it that they have to be cut with the same restriction enzyme? Well, the whole idea is, remember, I've got these sticky ends, right? And the sticky ends have a particular sequence. So if I want the sticky ends to be able to stick to another piece of DNA, I need the sticky ends to match. I need to be complements, and that's only going to happen if I've cut them with the same restriction enzyme. You can see that here, right? Here's my original DNA. Now, in this case, I'm sticking it back. You could, the idea, but, or actually, let's just look at this. Okay, so we've got this sequence right here, right? I cut between the G and the A, so now I have these sticky ends that are TTAA and AATT. So if I want this other piece of DNA right here to stick to those sticky ends, they have to have the complementary sequence AATT, which is actually what you get when you cut with that restriction enzyme only. So because of that, they would be able to stick in there, and that allows the DNA to bind in such a way that I can then seal it together. This is not the final sealing, but it's what allows them to stick to each other. So this is also a picture from your notes, and it might be a little easier to see here just because it's color-coded. But this is just sort of breaking it down into steps, like how do I make these recombinant plasmids? So how was, for example, your pGlow plasmid, how was it made? The one that you're going to use in your GFP lab next week. Well, step one would be I have to take the gene I'm interested in putting into my plasmid, and I have to take my plasmid, and I have to cut them with the same restriction enzyme. Next, I have to mix them together in the same tube. That's to allow those sticky ends to meet up with each other. Now, realistically, what's making the sticky ends stick together at that point is hydrogen bonds, which are not strong enough to keep that recombinant plasmid all together. So step 3 is I'm actually going to add another enzyme called DNA ligase, and that's going to reform the covalent bonds to seal the DNA back together. So again, what kinds of bonds does DNA ligase form? It is forming the covalent bonds, the ones between nucleotides in a single strand of DNA. Those hydrogen bonds, they're going to form just because the two strands are there and they have the complementary sequences. What we really need is like DNA ligase, which is like molecular glue, to really solidify that and form that bond so that the plasmid really is one cohesive piece of DNA again. All right, so we can now put this together with what we've already talked about for your GFP lab. These first three steps are, we've just talked about, how you create your recombinant plasmid. Right, we're going to isolate the plasmid DNA, and in this case the human gene we want to put in there. We cut them both the same restriction enzyme. You mix the DNA together. You're going to let them form their combinations. Now, keep in mind there's a lot of different combinations possible, right? A plasmid could just seal right back up again, so bind to itself, nothing gets in there. You could have one copy of the gene that you want go in there, two copies, it could go in backwards. So this is actually a little more complicated. I mean, they have to actually, once they do this, they have to kind of test to see which ones ended up like the recombinant plasmid they're looking for, which is one copy of the gene in the right direction in the plasmid. But assuming that they do that, then the next step would be to transform that plasmid into E. coli, which is what you're going to do in your lab next week. So what I'm kind of doing here is I'm just giving you the full picture of not just what are you doing in your lab, but how was that pea-glow plasmid even created? Because remember, we took a gene from jellyfish and we put it into a plasmid that came from bacteria, so that's not naturally occurring. What we can also use restriction enzymes for is restriction analysis, meaning we can also use them as a tool to find out stuff about a plasmid or any piece of DNA, really. So just to give you an idea, we can use restriction enzymes to find out things like how big is a plasmid, right? Because if we cut it up into a certain number of pieces and then we add them up, we can figure out how many base pairs total is it. Remember, not every restriction enzyme cuts every piece of DNA, so it is entirely possible that we have a plasmid that doesn't bind to and cut a piece of DNA. So another thing the restriction enzymes can tell us is, does this particular restriction enzyme even have restriction sites or places where it would recognize and cut this DNA? And how many places does it do that? Is it 1? Is it 2? Is it 7? We don't know. And then lastly, where are the restriction sites located relative to each other? Are they 300 base pairs apart? Are they 500? I want you to kind of remember this for now, but for now don't worry too much about it. We're going to revisit these ideas more when we talk about your next lab. But this was just sort of introduced to the idea of restriction enzymes. And later on, we'll talk about how we're going to use it in not the GFP lab, but the lab after that. Okay, so that's it for lecture. You can go ahead and put your notes away now.